Welcome back, fellow wizards, fellow scholars. It's now time for us to do homework 2, syntactic analysis. So let's get into it. I've already done these questions, but I'm just going to explain how I thought about these things. So if you don't want the answers right this second, give it a shot for yourself. So yeah, I'm just going to get into it. Here we go. So problem 1. Consider the following BNF grammar over the alphabet. Let n pq plus minus semicolon and equals, where the start symbol is s. Briefly identify 2 reasons why this grammar is not LL1. So immediately I can see ambiguity down the bottom. Basically, what's going to happen here is when you make your predictive parsing table, you're going to have overlapping first sets, which means each cell in the predictive parsing table has the possibility of having more than one production in it, which is not what you want. For it to be LL1, each cell in your predictive parsing table has to have only one or less productions. So I'll demonstrate that here. Here's our grammar on the side here. Then I've computed the first and the follow sets for each one, and we can use that to build our predictive parsing table. So as we're going through S and we encounter a let symbol, we can see that that let is in the first, so we can say S tends to SD or D. So immediately right there you have a bad. You have a big bad because there's two. You don't know which production to take there. Do you take S tends to SD or S tends to D? And then if we continue on, we eventually get down to all right. Well, let's do D. So if we're doing D, and we see a let symbol, then let is in the first of D quite obviously. So we just take D tends to let n equals E, semicolon. So that's fine, but I won't do this whole thing, but eventually you get down to E. So we start on E, and then when we run into a P, so we're here, we run into a P. It is in the first set, but which production do we take? There's 3 productions here. There's E tends to T plus E, E tends to T minus E, and E tends to T. Which one do we take? We can keep following this down, and it's not going to get any more unambiguous. So eventually, you follow this down, all the way down, and you get to V tends to PV, V tends to QV, V tends to P, V tends to Q. Again, that's 4 productions that you don't know which one you should be taking. So that would be down here in this cell here, when we run into a P symbol, which is in the first of V, it's completely ambiguous on which way to go. Yeah, so that's pretty much why this is not LL1. The question did say figure out 2 reasons why. I am not 100% sure what the second reason is, other than the fact that there's multiple, there is more than 2 ambiguous cells here. So I'm not sure if that's what it meant, but yeah, if anyone has any other ideas, please leave them in the comments. Yeah. Then for question 1b, is it possible to refactor this grammar into an equivalent one that is LL1? If so, give the new grammar. If not, explain why such a grammar cannot be written. As far as I can tell, you can't do that. You can't do it. Give it a shot. You cannot make this production any less ambiguous. So I tried rewriting this with, splitting out any like common factors. So I did something like, so here it is. So here's the production here. Tried doing something like this. V tends to PW or QW, where W tends to epsilon, chuck that in there, epsilon or PV or QV or P or Q. You can just see we're going in circles. Yeah, as far as I can tell, you just can't make that anymore ambiguous. But I may be wrong. If anyone can see otherwise, please let me know, because I definitely want to learn this stuff better. Question C, is the string let n equals minus PQP in the language of this grammar? If so, show the rightmost derivation of the string. If not, explain why it can't be derived. So yes, you break it up. It's definitely in the grammar. The derivation would be something like, so let me write out the string so we don't forget it. And then we'll do the derivation, which is S tends to D tends to let n equals E tends to let n equals T minus E semicolon. I'm just expanding. At this point, I'm just expanding the rightmost non-terminal. So the rightmost non-terminal here is E. I've expanded it to T minus E, and then I'm going to expand E next. Tends to let n equals T minus T. And again, we'll expand the rightmost non-terminal. Let n equals T minus V. Tends to keep going. We're going to let n equals T minus PV, semicolon, tends to let n equals T minus PQV. Again, we're just going to expand the V. Let n equals T minus PQP. We're almost there. Let n equals, since how do I do this? Since T can be the empty string, we can just get rid of T. And we're left with the final string, PQP. Done. Next one. D. Show the start state for the LR1 automaton for this grammar. Hint, remember to take the closure of items. So the start state would look something like, you would do S bar tends to dot S with the, followed by the end of input symbol. Can I tab in this? Probably not safe to do that. And then there would be zero, there would be nothing, there would be no look ahead symbol for this. Next would be S tends to dot D, because we're doing a predict, we're expanding here. And the look ahead symbol would be the end of input symbol, since it follows from anything that comes after S. The only thing that comes after S is the end of input symbol. Then S also tends to dot SD. Same thing, the only thing that comes after S is the look ahead symbol. And D, we need to predict D because we're up here. Tends to dot let N equals E. And now that is that's followed by the end of input symbol as well, because the only thing that follows D is the end of input symbol. That is we've just hit a terminal. So that's done. That's the first state of the LR1 parsing automaton. So the next step would be you would scan the let and complete. No, you wouldn't complete the. You scan through here. Then you'd predict the E, eventually complete the E, etc., and expand it up. So that's pretty much D. That's D done. Now, designing grammars. Question 2. Consider the basic symbols needed to represent simple arithmetic operations. The terminals are any number, open parentheses, closing parentheses, plus, minus, asterisks, etc., etc. And the operators are as follows in decreasing order of precedence. A restricted first example might be E tends to E operation E, or E in brackets, or some number literal. An operation can be plus asterisk and this little hat symbol. So immediately you can see that's wrong because it doesn't include these two symbols here. It doesn't include the minus symbol. Yeah, but whatever. We're continuing on. So it's got a few problems. It's ambiguous. It does not enforce operator precedence. Give an example to show that the grammar is ambiguous. So straight away. Well, actually, now that I think about this, it's probably an easier way for me to show this visually than just drawing it. But I will just draw it real quick. I'll draw this real quick, and then I'll show it visually with a table. So the reason why this is ambiguous is because there are multiple ways. So there are some strings where you can have multiple different trees for the same string. For example, if we have the number 2, let's go to that. If we have the number 2 plus 3 asterisk 4. There's two ways we can write this in a table. So in a tree, in a parse tree. So we start with E, which expands to E op E, E op E. Okay, now E is obviously going to expand to 2. So we can see that's pretty simple. E goes down to 2. The operation makes sense that it should be plus. That's the next symbol, so the chocolate is plus. Now we have to find something that accommodates this. Luckily, we can see that this is E op E. That's a terrible E. So all we have to do is expand that out to E, op E. Now we can simply sub in the values. So 3, op expands to asterisk, and E expands to 4. But the problem is this can be written a different way. So here we've had the plus symbol as the first operator, but it can actually be written like so. So we have to expand to E op E. Now we can actually say that this is our initial E op E. So we can, oh well, at least this is part of our initial E op E. So we can say that's 4, and the operation we're using is asterisk this time instead of the plus initially. And then we can just expand this into E op E. So E op E, and then we can sub in the values, the terminals, that is. Two perfectly valid parse trees for the same string, ergo this thing is ambiguous. Ambiguous as hell. So that's A, done. B, write an LR1 grammar for the full problem domain, including all the operators in the table with the appropriate precedence relationships and associativity. You don't need to show parse tables. So this is what I've come up with. And this handles the associativity in the 3 different stages of it. If anyone can see any problems with it, yeah, please let me know. I would love to learn more. If I'm making mistakes, I would love to know. I'm really not telling you guys the answers. I'm really sort of asking for your guys' input for help with this. So this is what I've come up with. So E turns to E hat T, and it also tends to T, so a new non-terminal that I've created, and T tends to the next level of precedence, which is some factor plus, sorry, getting ahead of myself, T asterisk some factor also tends to T divided by some factor, and T modulo some factor, and some factor itself. Then F tends to the next layer of operator precedence. I'm going to say F plus M, and F minus M, and also M itself. And finally, M can tend to some number literal, and E within parentheses. So this grammar, from what I can tell, is not ambiguous. And if I go to the next question, we can test this by showing the bottom-up derivation of this string here, which tests at all of our operators, essentially, using your grammar. So the way I did this is I could write out a shift reduce a shift reduce thing for this, but it's going to be like, I don't know, it's going to be like 20 or 30 lines or something, and I'm not going to do that right here. It's too long. I had done it in my book, but it's a mess because I'll make a mistake and then I have to backtrack 5 steps. Like, it's a mess. So what I did was I looked up this early front end website. You plug in your grammar on the left. You tell it what non-terminal you want it to pass. In this case, we want it to pass the starting non-terminal E, right? And then you can show it in charts, as in like the early pass states that it goes through, the completions, the shifts, the predictions and the completions, etc. There's a lot of lines. This is why I didn't want to do it. This is ridiculous. So, what I find most useful to look at is the tree. This shows you potentially multiple different trees. If there are ambiguous, if your grammar is ambiguous, there's going to be more than one tree. So you can see that this grammar is not ambiguous. It parses the input string given by the homework within one tree, and it seems fine. The only thing that I'm confused, the only thing that I'm, like not 100% on is the associativity of this hat symbol here. So the associativity of this symbol is supposed to be to the right. And I'm unsure if what I have here is able to handle that, whereas these operators have left associativity. So yeah, if anybody has any input, please let me know. But yeah, this tool is really cool for visualizing the trees. Thought I'd throw it out there. Right, question 3. LR grammars. It's the following grammar LA LR1. What about LR1? Explain. So, okay, so from the lecture notes, we have the quote, a grammar is LR1 if the action for each of its states is unambiguous. So immediately we can see that this is not LR1 because in the initial state, we're going to end up with an ambiguous choice to make, an ambiguous action, because we're going to have this. We're going to have an LR1 state, and we're going to have a diverging path to take when we encounter the A symbol. The idea is when we see an A symbol, we should be clear on which state we need to move to, but we're not clear because we don't know which production to take. We don't know what action to perform. The grammar is also not LALR1 because the last two productions have look-ahead sets that are not disjoint, meaning, well, they actually have identical look-ahead sets. So you can see what follows X, Q, or P. What follows Y? Again, Q or P. They share the same look-ahead sets. Therefore, this would cause a reduce conflict when we try to reduce the terminal A to one of these last two productions. So therefore, it's not LALR1 either. Number 4, early parsing. Consider the following grammar. Show the steps of parsing the string AAA using an early parser, including all the sets IJ. Alright, so we can do screenshot that. So we can do the first state, s bar to dot s, then s expands to dot s, s also expands to dot a, then a expands to dot little a. Then the next thing that we would need to do is predict. We first had to predict this s up here. So this would be state. Actually, the first thing we should do is scan this little a. So the next state becomes a dot. That means we can complete the big A. So A. So yeah, well, we've already done that here. So that gets completed. Then we can complete sorry, my bad. Complete A looks like this. That's what it looks like. So we complete that. Then we complete this S up here. So S tends to S dot S. We've completed this one. And then we need to predict this S. My bad. S tends to dot A. And then we need to predict this A. A tends to dot A. And then the next thing we need to do is scan the little A. I2 scans A tends to little a dot. Then we can complete that A. So completed that one. Then we can complete that S that we just predicted. So S dot completes this one. Continuing on, then we need to predict looks like I've missed a step. Yeah, we forgot to predict S tends to dot SS. That's fine. So we're left down here with dot with S. No, that's wrong because we can't complete that. So this S expands to this S here and this S here. We scan it, complete that S, then we complete this, right, yeah, we complete this S. This S gets completed. This S is still not completed yet because we need to complete that one there. Now we need to predict this S. So we're going to continue. Let's expand this as far as we can. So we're going to S tends to S dot SS, and S tends to dot A tends to dot little a, and then we go again. Next phase, we complete that A, complete this one, then we complete this next one. S dot S. Which still doesn't complete it. So we've now scanned 3 A's, and we still haven't completed all of these S's. So when we completed this one, we moved that up, we moved, so we completed this one, we completed this one, we didn't complete this one completely though. This S, we still didn't complete it. So what this is suggesting is that what I believe is happening is this isn't actually able to pass the AAA string, because we've now scanned 3 A's, we're not completed, and I would test this by plugging into the early front end and seeing if we can get it to parse that exact string. How do I do this specifically? I think I have to split them. Wait, maybe not. We'll try that. S also tends to A, and A tends to the character literal A. Does this work? We need to solve for S. Let me try splitting these up. Does that actually work? What if that's split? I'm not sure that's... I'm not sure that's right. If that is next to it, and then that. As far as I can tell, this at least doesn't pass the AAA string. But if you split up the tokens, it does parse ambiguously, which is fine. So what happens? So we go S tends to A, we complete the A, S tends to SS, we complete the A initially, and then we complete another A. Okay, so maybe... Okay, so I was completely wrong. It does complete it. You can ignore the... Okay, so you can, yeah, ignore some of the items, I guess. No, not the items. The steps, the scan steps, or the complete steps. Okay. So I guess I was completely wrong. Looks like what we do is go in here. Expand the first S. Complete it. Expand the next S. Complete it. Ignore. You basically ignore this S here. You completely ignore that. That completes it. That completes the first S. Then ignore this. Complete this. Sorry. This completes the second. Completes the second. Scans the second A here. Okay. I see how that works. So you can ignore. In other words, you don't have to fully complete every single every single one of these predictions. Don't have to come to fruition. Whereas you're still guaranteed to complete your 3A's here, which can resolve to completion of this and completion of this. Cool. It's a lot to take in, this stuff. So that's homework number 2. I'm going to be writing this up on GitHub. Hopefully someone will be able to correct me if I've made any mistakes. And then the next episode, I'll be actually working on the assignment. So assignment 2, it's going to be an absolute monster of an assignment by the looks of it. So wish me luck, and thanks for watching, guys. See ya in the next video.